So hello everyone and welcome to this week's Quantum Science Seminar, episode number 66, and it's all going to be about quantum error correction and superconducting circuits. Please remember, you're very welcome to ask questions. We're going to have two sections of questions throughout the talk, both after the introduction and at the end. So please do send your questions either via the YouTube live chat or to quantumscienceseminar@gmail.com. Remember, if you are posting questions, we do have a 30-second delay. So if we don't get to your question quite in the first section, we'll have it there also for the questions at the end. With that, I'm going to pass on to Letitia, who's going to introduce today's speaker.
So hello, everyone. It is really my pleasure to introduce our quantum science seminar speaker of today, Andreas Wallraff. So Andreas studied physics in London and in Aachen, and he did his PhD in Erlangen on the quantum dynamics of vortices in superconductors. And actually, I discovered today when looking at this, preparing this introduction, that he was the first to observe the tunneling and energy level quantization of an individual vortex, really a beautiful experiment. After that, he moved to Yale, where he studied the coherent interaction of a single atom with a single quantum electronic circuit. So this is really the birth of circuit QED. And after Yale, he joined ETH in 2006, first as assistant professor, then associate professor. Since 2012, he's full professor in solid-state physics. And in his group, the research focuses on the experimental study of quantum effects in superconducting electronic circuits, both for fundamental quantum optics experiments, circuit QED, but also for quantum information processing, which is really what we are going to hear about today on quantum error correction. And of course, for this beautiful research that he has been doing for so many years, Andreas got many prizes. There is a Nicholas Cooke Prize, European Science Prize in 2006, ERC Starting Grant 2009, Advanced Grant 2013, one that I remember actually because I was working next door at ETH Zurich. It's the ETH Max Rössler Prize in 2011, and also more recently the Helmholtz International Fellow Award in 2020. So with this, we are actually very much looking forward to learning the latest news on his group experiments and this quantum error correction very recent results. So Andreas, we are very much looking forward to your talk.
Yeah, thank you, Letitia, for the kind introduction. It's really a pleasure to be speaking at this online seminar series on quantum science. As Letitia pointed out, it will be on quantum error correction with superconducting circuits. So on my title slide here, you see a colorized microscope image of a superconducting circuit that we have used to implement error correction in the surface code with 17 superconducting qubits. Yeah? And the superconducting qubits are these yellow structures that you see on this title slide that are assembled to a larger network with lots of control and readout lines. And I'll explain to you throughout this presentation what error correction is about and why it's needed, and how we implemented it for the first time in a surface code with superconducting circuits. And as indicated in the abstract that was published with this talk, there is a paper that appeared 2 or 3 weeks ago in Nature on this subject. So this work is a collaboration between a team of experimentalists at ETH Zurich that are listed up here, and it's really a team effort. We've started to work on this project more than 6 years ago, funded by a US program, and everyone who's on this list really contributed. But I would still want to call out Sebastian Krinner, the main postdoc who pushed together with a graduate student, Nathan Lacroix, this experiment across the finish line with the help of everyone else listed here. We've also collaborated on this on the theory side with the group of Alexandre Blais at the University of Sherbrooke, and also with Markus Müller at RWTH Aachen. And as usual, yeah, as Letizia said, our lab at ETH has now been in operation since quite a number of years. I think it's 16 now. We've really been benefiting quite a lot from the efforts made by our many grad students and postdocs throughout the years. And so I'd like to thank all of those. And I think it's maybe also interesting to some of you what the students and postdocs now do. There's really quite a few of them who have faculty positions all over the world. And what we see more and more is that students and also postdocs move on to work with the quantum industry at either startups or also bigger companies. So that's also interesting to see. All right, so I'll begin with a little introduction to quantum information processing with superconducting circuits and why quantum error correction is needed, and then how we did go about realizing it in our circuit that you've seen on the title slide. All right, I guess most of you know about this seminal experiment in which the quantum computational advantage was demonstrated experimentally by Google, and this is now 3 years ago or so, and it's discussed in this publication that is listed down here. But it still, to some degree, represents the state of the art in quantum information processing with superconducting circuits quite well. So this experiment was done with 53 superconducting qubits that were assembled on a device that you see here on the right-hand side. And on this device, qubits were made that achieved state-of-the-art coherence times, and these qubits were operated with state-of-the-art single and 2-qubit gates. And on this device with the 53 qubits, Google had achieved to demonstrate a computational advantage of this quantum device in creating a complicated quantum state over a classical computer trying to simulate that quantum state. And so this is a quantum computational task, or the task that they have chosen to do was essentially to implement a random circuit that was assembled from about 1,000 2-qubit gates that were acted on these 53 qubits to create a complex multi-qubit entangled state. And then we're trying to simulate that entangled state on a conventional computer and then compare the outcomes of that simulation to the actual experiment realized on the quantum computing hardware. And they found that it was essentially close to impossible or even impossible on reasonable timescales to reproduce that complicated 53 qubit entangled state on a classical computer. So that was the first time that an experimental quantum computing hardware had outperformed even the largest conventional computer. So though this was done on a task which was really selected with a particular purpose of demonstrating the advantage of the quantum hardware over the classical hardware, but since the task was creating a complicated random entangled state, that is not particularly useful in terms of having solved an algorithmic problem more efficiently on a quantum computer than on a classical computer. So what is needed to go beyond this is actually to build systems with significantly more than 53 qubits, and also systems which can perform the quantum mechanical computations even at higher fidelities than what was realized in this experiment by Google. And I'll expand on that in a little bit in a second. And in addition, as you will see, if you look at how good the state was that this 53-qubit quantum processor created, you will see that the state fidelity was actually not as high as one would desire, and that actually points already at the need of realizing error correction in quantum computers, trying to correct errors that occur both by decoherence of the qubits that are used in this architecture, and also errors that are introduced by the control signals that one uses to actually perform single and 2-qubit gates. So error correction, implementation of error correction will be essential for realizing larger scale quantum information processing applications with superconducting circuits, and also in other systems, of course. So major advances in technology are required for that. So maybe to give you a bit more an idea what was achieved in this experiment by Google. So 53 out of 54 qubits were operational on such a chip that they have created. Here, the qubits themselves are indicated by these crosses, and couplers between the qubits are indicated by the colored boxes. So on this device, Google was able to operate 2-qubit gates between any pair of qubits that are coupled to each other with a gate fidelity that was better than 1%. Google was able to perform a single-shot qubit readout on every one of these 53 qubits with a pretty decent error margin, which was only 4%. And then they have implemented in a gate sequence that had a depth of 20 gates in sequence between any pair of the qubits that you see on this schematic on the right-hand side, which resulted in sort of a total number of about 1,000 2-qubit gates implemented here. And the state that was created by operating this gate sequence was hard to simulate, as I mentioned, but if you then compared how close the created state was actually to the ideal state that would be created in case there was no decoherence, no single or 2-qubit gate errors, no errors in the readout, one had realized that the state fidelity was only 10 to the -3. And where the fidelity that you would actually want to achieve is unit fidelity. So the created state was actually quite far from what an ideal system would have produced. And that indicates that if you want to run a quantum computer on a problem where you require computational accuracy, there will likely be no way around using error correction in the end for deep circuits and large problems. And so these limitations of this fidelity here were essentially imposed by the coherence of the qubits and by the finite control accuracy that one can achieve. So this then really calls for trying to realize a universal fault-tolerant quantum computer through quantum error correction. So these days, I think there's two major goals that get followed in groups, both at universities and at startups and also in industry, trying to explore superconducting circuits for quantum information processing. And one direction is certainly to go further along exploring systems with 50 plus qubits to realize so-called noisy intermediate scale quantum algorithms. That's one of the big branches or directions that gets followed by many different labs and companies. And the other direction that actually has regained focus in the last maybe 2 years, I would say, or maybe even a bit longer, is the quest for realizing fault-tolerant, error-corrected universal quantum information processors by encoding logical quantum information into a set of superconducting qubits. And this diagram here on the right-hand side that you will see actually quite a number of times throughout this talk today, where every circle, every colored circle represents a physical qubit. And in a logical qubit, you would encode quantum information not in a single physical qubit, but you would distribute it in a clever way across many physical qubits to encode a logical qubit. And how that works, I'll explain to you throughout this talk. Good, so I should maybe also mention a caveat here. There's different approaches to quantum error correction. And the one that I'll be discussing here is one where the logical qubits are realized in a qubit-based encoding, where you essentially use a set of physical qubits to encode the logical qubit. There is an alternative, namely one which uses a continuous variable encoding, where you essentially use harmonic oscillator states and encode quantum information in cat states or so-called GKP states. And there's also very nice work on this topic with superconducting circuits and also in ion traps, but I'll not cover it in this presentation. But you might want to look up these approaches, which are also very promising and which also perform very, very well also in comparison to these digital methods. Okay, so let's maybe get back for a second to this question: why is error correction needed at all? Yeah? So just remember that in a physical qubit, you store quantum information in the states of all the possible states of a physical qubit. So you have On the right-hand side here, you have a Bloch sphere representation of these physical states. And the basis states, the computational basis states, are the eigenstates of a Pauli Z operator, which is stated here. So the physical ground state is can be represented as an arrow pointing to the north pole of this Bloch sphere here, and the physical excited state is an arrow pointing to the south pole. And in any physical quantum system, the excited state after some time will decay back down to the ground state due to spontaneous emission. And that spontaneous emission is due to the coupling of the physical quantum system to the vacuum fluctuations. And so even though there is maybe some physical entities like nuclear spins, for example, which couple very weakly to vacuum fluctuations, there's always a time scale on which the qubit will decay from its excited to its ground state. And in particular, in superconducting circuits, these typical decay rates or decay times are maybe on the order of say, a few tens or a few hundreds of microseconds, at which ones turn into zeros. And that's obviously an error source. So say, even if your logical decay time or if your physical decay time is long because you have a qubit which couples weakly to the vacuum fluctuations, a second source that leads to errors in this computational basis is the fact that you may have control inaccuracies. So while you try to turn zero states into one states by applying electromagnetic fields to your qubit, this may not happen with arbitrarily good accuracy. And sometimes when you want to prepare an excited state, for example, maybe you prepare it only with a fidelity of 3 nines rather than infinitely good. And so that will also accumulate an error, which you would want to correct if you're able to do so. Another source of errors could be that there's, for example, thermal excitations because your qubit is not at zero temperature, but couples to some bath, and that could also lead to excitations from zeros into ones. So that's one sort of error in the computational basis. And this error we also know from conventional or classical systems. Yeah, when you represent classical information in forms of bits, zeros and ones, also over classical channels, these zeros can turn into ones if the channel is noisy enough. And one of the ways how you can characterize the rates at which ones decay into zeros is to measure the expectation value of the physical qubit Z operator, which represents essentially the or which is a way to determine the decay rate of the qubit from its excited to its ground state. So this is something that is shown here for one of the physical qubits on the chip that we will be discussing later. And this physical decay, or this T1 time, which characterizes the physical decay of our superconducting qubit here, is around 30 microseconds or so. And the goal of doing quantum error correction is to make that effective lifetime of a physical qubit larger by not using that physical qubit, but encoding quantum information in a logical qubit that is assembled from many physical qubits, and do that in a way that you actually gain in performance over the physical qubit. So what is also important in quantum information processing and in quantum error correction is that there is a second type of error. There's not only bit flips that turns zeros into ones, but since quantum computers also make use of superposition states, so coherent superpositions between zeros and ones with a determined phase factor, for example, with a plus phase factor or minus phase factor, there's also phase flip errors that can occur. So coherent superposition state 0 plus 1 could turn into a coherent superposition state 0 minus 1. And these superposition states, these particular pair that I've shown here, are eigenstates of the Pauli X operator. And phase flip errors can also occur in quantum computers, and these could, for example, originate from fluctuations in the fields that create the energy splitting in your qubits that would lead to phase fluctuations, for example. Or again, your quantum control of the single qubit state might be limited. So while you try to prepare a given superposition state, you might make a small error, and these small errors may accumulate. And if you had a chance to correct for this accumulation of these small errors, you would do that. And clearly also these superposition states suffer from energy relaxation, the mechanism that I've just explained before. And a way to look at the at the phase coherence in a single physical qubit is, for example, by doing a Ramsey oscillation measurement that is shown for one of the physical qubits on our device here, for which the coherence time, the phase coherence time, was measured to be, again, a little bit more than 30 microseconds in this instance. Okay, and so one wants to fight these two types of errors, phase flip errors and bit flip errors. And the way to do that in a so-called surface code is to use an extra set of qubits. There's one set of qubits, the red ones, which you see here, which are used to encode the quantum information in so-called code qubits or data qubits, which are shown in red. And then there's a second set of qubits, which are shown in green and blue, which are auxiliary qubits that are used to actually help to detect whether an error occurred on any of the data qubits. And these helper qubits occur in these two different types, namely the green and the blue ones. And those indicate that one of the type of the helper qubits identifies bit flip errors and the other one identifies phase flip errors. And so now the clever thing to try to do in quantum error correction is that you somehow need to notice that an error has occurred by performing some type of measurement on your logical qubit that does not affect the quantum information that is stored in that logical qubit. Yeah, if you would just take a physical qubit and prepare it in a superposition state, and then you would measure that superposition state in a Z basis, that measurement would project the qubit state out of that superposition state into one of its computational basis states 0 or 1, and thus affect the stored quantum information. And therefore, in error correction, you need to find a way how you would actually encode the information, perform measurements on these encoded qubits that look at a clever property of those states without affecting the stored quantum information. And the way to do that is to encode the logical qubit in a set of physical qubits and use certain symmetry properties of the state of these physical qubits that can be measured without affecting the logical quantum state that is stored in this set of physical qubits. And the property that we actually choose to look at is the parity of the data qubits. So the idea in the error correction scheme that we have realized according to the surface code is to store all quantum information in a set of physical qubits in qubit states that have all a given parity, and we choose even parity to do that, and we can then verify whether all our data qubits remained in an even parity state without affecting the logical qubit information that is stored in these qubits. And I'll give examples of what that looks like in our actual device. So what is interesting about the surface code? So the error correction scheme that we've implemented is the surface code. It's a specific encoding of logical information in physical qubits. And the surface code inherits some topological features from toric codes that it was derived from. And these topological features also allow one in a system where the logical information is distributed over many physical qubits to still correct errors by only operating locally on individual qubits in this larger lattice or in this larger area of qubits. So that's one special feature of this surface code. And also that the qubits can be laid out in a planar geometry here, say, and that's certainly good for devices that are built in say, circuit-based or solid-state-based technologies where you would place qubits in a regular array, which is a good idea for superconducting circuits or, for example, for spin qubits. Yeah? And ion traps, for example, where you have a sort of ions in a long chain and can couple any ion to any other ion, you might be more flexible and creating the right connectivity for operating logically between different ions. But in the solid state, actually, this square array is a good idea. So what is also special about the surface code is that it has a very large error threshold. So the error threshold defines how good the individual components of your surface code need to be, how good the single qubit gates, the 2 qubit gates, the qubit readout needs to be, so that you have a chance of, when assembling these complicated structure, to encode a logical qubit, for that logical qubit to actually perform better than any of the individual physical qubits. And for the surface code, that threshold is about at 1% for every component, for the single qubit gate, for the 2 qubit gates, and for the readouts. And as soon as that's the case, when you assemble a logical qubit from many physical qubits, you have a chance of actually getting an improved logical qubit performance, improved over the performance of the physical elements. And the surface code is the code which has the highest threshold in comparison to any other codes that have been invented so far. So therefore, it's a good idea to try to implement this surface code. All right. So what are the elements of this surface code? So we've looked at this picture here already a little bit. You see this array of qubits. The red ones are the so-called data qubits, or which are sometimes also called code qubits, and they form this square array. And what you see here is an array that has 5 by 5 data qubits, so 25 in total. And this forms a so-called distance 5 surface code. This 5 by 5 set of data qubits is augmented by the auxiliary qubits that I've already mentioned. And of the auxiliary qubits, there is 5 by 5 minus 1, so that's 24. So you see a total of 49 qubits here, forming a logical qubit in a so-called distance 5 surface code logical qubit. And the green and blue qubits are used to measure these parity or these symmetry properties of a set of data qubits that the auxiliary qubits are coupled to. And for example, if we single out this Z auxiliary qubit here, it's coupled to 4 neighboring data qubits that form a so-called plaquette. And this auxiliary qubit is actually used to measure the parity of the 4 neighboring data qubits that it's coupled to. And this kind of parity measurement, there's different ways to look at it. One way to look at it is to define it as a measurement of the product of 4 Pauli Z operators, Z1 times Z2 times Z3 times Z4, of the 4 neighboring data qubits here. And so this is the measurement of this operator here, this product of the 4 Pauli Z operators would be called a stabilizer measurement. And now you could think about how you would implement such a stabilizer measurement on your device. You need to measure this operator for individual qubits. We know how to perform such a measurement in most physical systems, but to define a physical measurement that actually extracts that information through a measurement apparatus directly is typically difficult. And therefore, one has actually come up with an auxiliary qubit-based method to measure this operator here effectively. And this auxiliary-based qubit method is explained here. So here you see this 4 neighboring data qubits of such a plaquette. And what one does is one prepares this auxiliary qubit in the ground state. And then one runs logical C0 gates between each one of the data qubits and the auxiliary qubits in a sequence one after each other, so that at the end of the sequence of 4 2-qubit gates, every data qubit has interacted once with this auxiliary qubit. And so this actually performs a parity measurement of the 4 data qubits that are connected to the auxiliary qubit in the Z basis. And I'll give you an example that will make that more explicit. And the surface code has auxiliary qubits in the bulk that sit sort of in the inner part of this lattice. And there's also auxiliary qubits that sit at the border of this lattice. And these auxiliary qubits are coupled only to 2 data qubits, and those are then called so-called weight 2 stabilizers, while the auxiliary qubits that sit more in the center are called weight 4 stabilizers. And so since there are not only bit flip errors, but also phase flip errors, there's a second type of auxiliary qubits that again couples to 4 nearest neighbors data qubits. And there you essentially do a measurement not of this product of 4 Pauli Z operators, but you perform a measurement of the product of 4 Pauli X operators. And this can essentially be realized in the same auxiliary qubit-based method by flipping the basis of the data qubits by applying pi-half pulses to each one of the data qubits. And then the same sequence of C0 gates essentially measures the parity of the 4 data qubits now in the X spaces. And so these types of parity measurements then allow you to detect whether the neighboring qubits, both in the Z and in the X spaces, are still in the parity state that you intended them to be. And your error correction will work in the following way, that these stabilizer measurements verify if the correct state is still preserved, the one with the intended parity. And if this measurement indicates, oh, the parity has changed, you know, oh, there was an error, and you now need to correct it. And the goal of the surface code is to find out, to have enough information available that also allows one to determine where the error had actually occurred. But maybe before we get into that in the next part of the talk, I think here's one important realization. Namely, if you want to do these stabilizer measurements, they're assembled from a series of 2-qubit gates and a series of single qubit gates and a measurement. And for determining the parity accurately, you are then required to do very good 2-qubit gates, very good single qubit gates, and a very good readout all the time that you run the error correction code on your physical qubits. So this has quite high demands on every single element of the realization of the surface code. So you need to have good elements to assemble your surface code from. And in particular, you also require a good readout of these auxiliary qubits every time you want to determine the parity of the 4 neighboring data qubits. Okay, so here's an easy example for weight 2 parity measurement, just to make it explicit. So for example, if you have the 2 data qubits in the 0 state and the ancilla qubit or the auxiliary qubit also in the 0 state, you run 2 C0 gates, nothing happens, it stays, the auxiliary qubit stays in the 0 state. Then if you have 2 data qubits in the excited state, which is also an even parity state, the first C0 gate will flip the auxiliary qubit from 0 to 1. And then the second C0 gate will flip it back from 1 to 0. So effectively, the auxiliary qubit stays in the 0 state. And now if you look at that, you could see that anytime that you have an even number of data qubits in the state 1, yeah, the series of C0 gates will always leave the auxiliary qubit in state 0. So now if an error would occur on any of the data qubits in the state 1, then this would turn from an even parity state with an even number of ones into an odd one, because now you have a 0 and a 1, and this odd number of data qubits in the 1 state would be indicated by the auxiliary qubits now to flip from 0 to 1. And this you see in this next slide here, where you see the example for the combination 0, 1 and 1, 0, where you see that in the end, the auxiliary qubit has moved from state 0 to state 1, indicating a parity change in the data qubit. And in this way, you would detect that a bit flip has occurred on one of the data qubits. And if you do the same thing in the X spaces, you can also detect whether a phase flip has occurred in one of the data qubits or not. Okay, and that's essentially what you do in a surface code. And a surface code on this whole set of 49 qubits that I've showed to you, you would run these stabilizer measurements on each and every plaquette in every round of the error correction cycle. And that's essentially what needs to be done to implement an error-corrected logical qubit. And I'll give you maybe one more example, and then maybe it's a good time to take some first questions. So 2 years ago, we realized a small version of a surface code with only 7 superconducting qubits that has 4 data qubits that you see here, and 3 auxiliary qubits. You have 1 that is a weight 4 stabilizer and 2 that are weight 2 stabilizers. And so here are the operators that you would measure are listed here. And so this is a small enough surface code that you can still look easily at the states that you use for encoding the logical information. And so here is a picture of the logical 0 state, or it's written down, or it's a superposition between all data qubits being in the ground state and all data qubits being in the excited state. So this is clearly an even parity state. Now you could ask how you can create an excited logical state out of that. And this can be done by operating with a so-called logical bit flip operator on this state here. And this logical bit flip operator would either flip the first and the third qubit from 0 to 1, or the second and the fourth qubit from 0 to 1. And so these happen to be indicated in this picture here as the operators that lie along a line that crosses through this 4 data qubits. So if you do that, you see that now the excited state looks like this. So it still has an even parity. So that's what you want. Yeah? And this parity measurement will now not be able to distinguish between the 0 logical and the 1 logical. So now you also know how you would create a logical superposition state. It's just a superposition between the 0 logical and the 1 logical. It's just a sum of these 2 states that you see here. It's still even parity. And now you could create a minus logical state by operating with the logical Z operator on this logical plus operator. And the logical Z operator is the product of Pauli Z on the first qubit and the second qubit, or on the third qubit and the fourth qubit. So that's the Pauli operators that lie along a line through D1 and D2 here, or D4 and D5. So when you do that on that state, and maybe that's something by staring on the slide at the end of the talk, you can verify that. That will then swap the signs of these last 2 state components and create the minus state. And so that's how you would encode in this very small surface code the logical information. And here you can now verify that all these logical states have all even parity. And if one of the qubits would flip its state, it would turn any one of these states into an odd parity state, which your stabilizer measurement would detect, and which you could then go ahead and correct for. Okay, so I think now would be a good time to take some questions if there are any.
Thank you, Andreas, already for the very nice introduction and smooth one. So indeed, there are some questions. Let me start a bit with the general ones regarding the Google experiment. So you mentioned that the fidelity was rather low. So in which sense does one then argue that the computer made the calculation? Namely, how would one know the result of the calculation if one were not able to calculate it classically?
So this is, if you look at the paper or so, you see that this is taken into account in their evaluation. So even though the fidelity is low, you would say, okay, good, that it has only a chance of 1 in 1,000. That's one way to express that 10 to the minus 3 fidelity to get the state exactly right. Or it was still hard enough for the classical computer, even on this level of 1 in 1,000, to determine that state correctly. Yeah? And if the fidelity would be higher or so, then it would of course be even harder to classically simulate that. But it was like the experiment was still big enough and for the conventional computer to have a hard time simulating that. And in the last 3 years, people developed better methods to run conventional computers more efficiently to get closer to the states that were simulated here. But for example, in that regard, it's important to see that both Google and then also the group of Zhanwei Pan in China, they're looking into making larger devices, and as soon as you add a few more qubits, it will get exponentially harder for the conventional computer to simulate these types of states. So with smallish hardware effort, you can do something that is very hard to reproduce with conventional methods.
Thank you. So clearly, we will need error correction for arbitrary precision quantum calculations. But what do you think the prospects are for doing useful calculations, and useful in which sense, with larger scale quantum systems, but without error correction?
I think it's going to be interesting, and maybe on the quantum simulation side, you can learn things that will be useful. I think, yeah. Like I think you can probably answer interesting physics questions in this context. To perform good sort of numerical calculations with a given accuracy that you want on a scale that then will be interesting to a real application, I think this will be a very big challenge. So I think in the end, it's clear that error correction will be needed to get precision results for anything where numerical accuracy is really desired. For example, in quantum chemistry, where you want to calculate some property with a certain accuracy, or if you want to have a or if you want to solve an optimization problem and make sure that it's close to the optimal solution. So I think then in the end, I think it's interesting to think about these other methods that improve the accuracy of the results. And there's really interesting ones developed by many of the players in the field. But what is ultimately needed, I think, is error correction on these systems so that you can run deep and long circuits or with large numbers of qubits. And that will be a major challenge that we all have to still solve together.
Thank you. So we have a question from the YouTube chat from Alexander Kordiuk. He's asking how the decoherence parameters, such as the decay time, for example, in a superconducting qubit, depend on parameters of superconducting elements, such as, for instance, the superconducting gap.
Okay, so maybe if it's related to the superconducting gap, there's a question: does it help to have higher gap materials? For example, sometimes the question comes up, but would it be good to use high temperature superconductors, for example? There's decoherence mechanisms that depend on the gap energy. For example, if they're limited by quasi-particle generation, that is when high energy particles hit your circuit, and that could be photons, infrared photons, for example, from the environment. And more of those these infrared photons will create more quasi-particles the lower the gap energy of the superconductor is. So there's some relation to the gap energy, but it's important in many different contexts. And usually superconducting circuits suffer from a wideish range of decoherence phenomena. Some of them relate to the circuit design, and those the designers of the circuits can try to handle. And then there's maybe the most difficult ones to deal with is ones that relate to surface defects. And currently, I think the biggest culprits are actually maybe a combination of the quasi-particles, which I've mentioned, and surface defects on these devices.
Thank you. And regarding the surface code, so is the surface code that you are presenting the best choice for error correction in near-term quantum computers? Or is it the most straightforward to implement? And are there other codes that might give better performance?
I think one of the aspects that is special about the surface code, as I mentioned, is that it has this high error threshold. So it's the one that can deal with the worst hardware to some degree. Yeah, and so that's good. There's other codes that have much lower thresholds, so that will make it harder. I think that's a very good feature for the surface code. There's one question, for example, if you had sort of biased noise in your architecture, for example, if bit flip errors were much more likely than phase flip errors, or the reverse of that, then you can try to develop codes which make use of that. And certainly looking into codes that are vary of the performance limitations of the devices makes sense. Interestingly, in our device, we in the end found that at least in the way we operate the device, that the errors were pretty equally distributed among phase flips and bit flips, and that has to do with a specific way on how we run these stabilizer measurements. But I think the surface code is one of the choices that is particularly amenable to architectures where you lay out qubits in a square array as well. So I think it's certainly one of the approaches that needed to be demonstrated, and that is a good choice because of the error threshold.
Thank you. We have a couple of more questions from the YouTube chat. First one is by Vivek Dande, and the question is: how does error correction schemes compare between superconducting and semiconducting quantum computing? I guess
semiconductor quantum computers. I do think that so since they're the semiconducting ones will be qubit based, so I do think that likely one would use very similar approaches, and that's maybe also why surface code is interesting, because one can probably learn something from the surface code implementations that are realized in one architecture for another architecture. So I think the same reasoning will apply eventually also to semiconductor devices. Say if there's more progress with spin qubits, for example, for the same reasoning, you will want to try to implement error correction on these spin qubits, and you would probably end up at similar choices in the end.
Mm-hmm. Okay, another question from the YouTube chat from Uday Raifin. What about using different types of Josephson junctions, like weak link graphene Josephson junctions?
Mm-hmm. So that maybe then boils down to what different types of superconducting qubits could you use, and could you get different control parameters or ones with better performance? And there are certainly interesting alternatives that get explored, creating a weak link, for example, through other circuit elements. And one particularly interesting aspect is maybe to take circuit elements that can be voltage controlled. In superconducting qubits, many of them use some form of magnetic field or flux control. And if one can control the Josephson energy through applying a gate voltage rather than through applying a magnetic flux, that can have advantages. So that's actively being explored. So there's different types of qubits that get looked at. So we've done our experiments with transmon qubits, which are probably the most common type of qubit that is used in superconducting circuits. But there's also different kind of tunnel junction based superconducting qubits, and there's also more exploratory research on trying to use different types of weak links. At the moment, I think though that the tunnel junction based ones have the best coherence properties.
Okay, thank you. And actually a third, so another question from the YouTube channel from Thomas Cosley. So do you believe that superconducting quantum computers can become all-purpose machines for quantum computation, or does a hybrid over several architectures like MBs, colatoms, photons, etc., be more likely?
Yeah, that's a good question. I think the hybrid systems are very interesting. I find them interesting to explore. We've done some work in that direction ourselves. I think all the technologies individually are typically quite complex. And we need to look at how one would combine them with an advantage. Yeah? And to combine two complex technologies with each other is typically extra hard. Yeah? And this one has to take into account when one combines those. Yeah? And I think this can pay off when one of the technologies really provides a significant advantage over the other. Yeah? So maybe one scenario that one could think of, maybe one can realize a quantum memory in a nuclear spin in some solid. Yeah? And if one finds a clever way how to map the quantum state from a superconducting qubit that is stored in sort of in conventional electromagnetic degrees of freedom into a nuclear spin, that could be interesting. Yeah? And but it needs to combine these technologically different systems with each other.
Okay, thank you. Yes, there are more questions, but maybe not to cut too much the flow of the talk. I would suggest to continue.
Good. Okay. Yeah. Thank you very much. So I've essentially explained a little bit how the surface code works and given you this example for the so-called distance 2 surface code. What is special about this distance 2 surface code that we've done an experiment on is that actually has only 3 of these stabilizer measurements, and these 3 measurements can be used to detect whether an error has occurred. But the 3 measurements are not enough to determine on which of the code qubits the error has occurred. And the smallest surface code on which that is actually possible to detect where the error has occurred, which is a requirement for actually correcting for the error, is the so-called distance 3 surface code. And that's what's on this next slide here. So here the distance 3 surface code has 3 by 3 data qubits, so 9, and 3 by 3 minus 1 auxiliary qubits. So the quantum information is encoded in 9 physical qubits, and the states have the same properties that I discussed just for the distance 2 code, but extended to distance 3 with 9 data qubits. Here again, then the logical operators are sort of strings of Pauli operators acting on individual data qubits. So for example, the logical Z operator could be the Z1 times Z2 times Z3. and the logical X operator could be X1 times X4 times X7. And if you would apply those to any of the basis states, you would flip from logical 0 to logical 1 or from logical plus to logical minus. And the distance of a surface code also actually corresponds to the minimum number of Pauli operators that you need to implement such a logical gate, which is 3 in the case of a distance 3 surface code. So there's 8 auxiliary qubits that are used to perform these parity or stabilizer measurements that I'd mentioned. And these parity and stabilizer measurements detect the parity of the data qubits that form a plaquette together with this auxiliary qubit. And the plaquettes are shown here by these colored backgrounds, blue for the X stabilizers and green for the Z stabilizers. And in this distance 3 surface code, you now see that there's 4 Z stabilizers and 4 X stabilizers. And each 2 of them are weight 4, so involving 4 data qubits, and 2 of them are weight 2 involving 2 data qubits. And the weight 2 ones are at the edges of the surface code, and the weight 4 ones are sort of in the bulk of the surface code. So here you actually now get a nice view of the device that we've made to implement this distance 3 surface code with 17 superconducting qubits. And in some sense, you should feel a little bit privileged to get that close look at such a device, because typically, if you look at work from other labs on devices on this size scale, you typically don't get to see the device itself, which would be very interesting to actually take a look at. So you can take a close look at it here and also in the paper. So every one of these yellow structures is a superconducting qubit. It's made from a shaped patch of metal on a silicon substrate. And that patch of metal is shunted through a Josephson squid made from 2 Josephson tunnel junction to the ground, which is the surrounding gray area. Then you can control the quantum state of every one of these superconducting qubits by applying microwave pulses through these pink transmission lines, where you apply gigahertz frequency, nanosecond long phase controlled microwave pulses through each one of these lines to each qubit individually. And that gets used to perform single qubit gates. Then the green lines here are used to apply short current pulses to each qubit. And these short current pulses create a magnetic field next to the squid loop of the qubit. And that magnetic field tunes the transition frequency of the qubit. And we actually initiate gates between neighboring qubits by tuning the relative frequencies of 2 neighboring qubits. And this tuning of the transition frequency when the 2 qubits are brought near resonance actually mediates an interaction between qubits that are connected by one of these coupling waveguide structures that you see in light blue here, that actually form such a square array. And then one aspect that is very important, in particular in quantum error correction and in the surface code, is that you need an ability to perform high fidelity and fast readout of every one of the qubits, in particular the auxiliary qubits that allow you to measure the parity of the neighboring data qubits. And for that purpose, every one of these 17 data qubits has a superconducting resonator connected to it. That's another strip line, a lambda quarter microwave frequency resonator here shown in red. And that is coupled to a so-called Purcell filter to be able to have a strong coupling of this readout resonator to the superconducting qubit, but avoid the Purcell decay of the qubit into that readout resonator that would lead to enhanced relaxation. And so every qubit has its own dedicated readout resonator. And then one aspect that is special here is that in this architecture, 4 or 5 qubits get read out through the same transmission line. So you see here this dark purple transmission line that passes by a set of readout resonators. And there you can actually apply a frequency multiplexed simultaneous pulse to each one of these microwave pulse to each one of these readout resonators, and that are staggered in frequency and essentially read out a set of qubits simultaneously. And there's 4 of these readout lines. So you can read out on 3 of those lines, you read out 4 qubits simultaneously, and on one of them you read out 5 simultaneously. And so now you wonder, where's my surface code structure? So we've indicated here the plaquettes. You see on the vertices of the plaquettes, there's the data qubits. So there's 9 of them, 3 by 3. And in the centers of the plaquettes, there's the auxiliary qubits. And you see the 4 weight 4 auxiliary qubits here in the center. And then on the edge or on the boundary, there's 4 weight 2 auxiliary qubits that are used to perform weight 2 stabilizer measurements. Okay, so how good is this device? So the average energy relaxation times and Ramsey decay times are around 30 microseconds or so. The single qubit gates have errors that are about 10 to the minus 3, so 0.1%. The 2 qubit gate errors are on the order of 1.5%. And the durations of the gates are indicated here. And on the left-hand side, what you see is actually a cumulative distribution. So that's the integrated histogram of the distribution of these gate errors. And that shows you a little bit which gate errors occur with which probability. And you see that there's typically some outliers. So the average is pretty good, but then there are some gates which are significantly worse than others. So maybe the worst 2 qubit gate here has maybe an error of more like 3 or 4% even. And what is also important in the surface code is that you need to be able to perform good readout of the auxiliary qubits in particular, because those are the ones that are used to perform this stabilizer measurement. And these readout errors are around 1% when we discriminate 2 states of our qubits. But our readout also has the ability to discriminate a so-called leakage state. So that's the second excited state of our qubit. That is particularly detrimental for the surface code, because if you leave the computational subspace, then your surface code can't figure out what errors have occurred. So it's important to catch those and be able to deal with them. So overall, I think this is a very nice device. Or so it's maybe there's other devices from other competing labs that have individually better parameters, but this is very well rounded and actually performed quite well in the surface code experiment. So here's maybe a few more pictures what then things look like. You've seen the device previously. So here's the chip that you have seen in a sample mount that is the size of a ice hockey puck. So I tend to play ice hockey, so I know what this looks like. So that's about this size here, maybe 10, 15 centimeters across with a 1.4 by 1.4 centimeter large chip in the center, and there's 48 connectors connected to it through which we apply all the signals that are needed to control this chip. Then this goes into an electromagnetic shielded housing and connects through microwave cables to room temperature electronics. And so this then sits at the base plate of a sort of a biggish cryogenic system that cools the qubits down to 10 millikelvin about, and then you see lots of wires coming up through the different temperature stages of the dilution refrigerator, moving towards room temperature, where the signals are then connected to microwave frequency electronics. And here you see a picture of the actual setup that this experiment was done in. So there's a large dilution refrigerator. The cables come out at the top and then are moved over to a rack full of instrumentation. And this instrumentation has the readout electronics in its lower part. There's microwave sources below that. And then there's arbitrary waveform generators that do all the pulse modulation and the qubit transition frequency control. And you see that starts to be a sort of electronic-wise a major experiment with quite a few cables that need to be connected from room temperature back down to your qubits. All right, so maybe, so this is my slide that puts this into context with other work. So obviously quantum error correction didn't start with this experiment. There's lots of work that led up to this. And so the work is maybe categorized in 3 different steps. So there was initial work where single bit or phase flip errors have been detected and then also corrected individually. Then there were experiments where it was first possible to correct both bit and phase flip errors and detect them, but only in single cycle experiment. And in a quantum error correction system, you need to be able to continuously detect errors and then correct for them. So repeat the stabilizer measurements essentially for infinity. And then there were first repeated error detection experiments on small codes, on small surface codes. And I mentioned the simple one that our lab had done 2 years ago. And then actually in the past year or so, there was quite a bit of progress on realizing repeated quantum error correction in distance 3 codes, both in ions and then also in superconducting circuits. So the ion experiment was sometime in summer last year. And then towards the end of the last year, the end of 21, there was our experiment and an experiment from John Y. Pun's group. And now since March this year, there's also a nice experiment by IBM. All right, so maybe, now let's put all these elements together. So the key element are these stabilizer measurements, the ones that determine the parity of these data qubits. And so now you know how that works. And maybe one thing that I should still explain, that in our actual devices, we are not realizing C0 gates in the 2-qubit gate between our data qubits and the auxiliary qubit, but we have C phase gates that are implemented on our device. And essentially, there's a different way to look at this parity measurement. You could look at it as a generalized Ramsey experiment where you prepare your auxiliary qubit in a superposition state, and then you run 4 C phase gates in sequence. And every time the data qubit is in the excited state, it will actually imprint a -1 phase factor on the auxiliary qubit. And if you have an even number of -1s, there will be no effective phase on the auxiliary qubit, while when the number is odd, there will be an effective phase that you can then determine in this Ramsey experiment. And you do that without basis change on the data qubits, and that does a Z stabilizer measurement, and with basis change, it does an X stabilizer measurement. And one aspect that is also quite important in our experimental setup is that we then augmented this gate sequence by another set of pi pulses on the data qubits. And this essentially performs a spin echo, and that echoes out some of the residual interactions that we get between our data qubits, so-called ZZ interactions that are mediated between our qubits when nominally the coupling is off, when they're largely detuned from each other. And likely these spin echo pulses, they also help to symmetrize the errors between bit flip and phase flip errors in our setup. Okay, and then the first thing that you do is you characterize your stabilizer measurements and see whether they can detect the parity properly. And therefore you prepare your data qubits in a plaquette in all 4 basis states, in all 2 to the 4 basis states. And so here's an example of that. And then you run your stabilizer measurement. So the 2 to the 4 basis states are listed here. You see all the ones with even parity. So the ones that have an even number of 1s present a stabilizer value of +1, which indicates even parity. So here in the middle, you see all the ones which have 2 1s. And then at the end, the one which has 4 1s. And then the first one is the one which has no 1s at all. And all the odd parity states get measured with a stabilizer value of -1. So that essentially executes the gate sequence on such a green plaquette as it's shown here. And you can ask yourself, how well does that work? So the experimental stabilizer error that was evaluated from this data set is about 7%, while the simulated one from a master equation simulation is about 4%. So we have a sort of a reasonable agreement between our measurement result and the simulations. And so since there's 8 stabilizers, what we do is we prepare on every plaquette, we prepare all the basis states and then test the stabilizer measurement, and we look at how well that works. And the small stabilizers of weight 2, they are better than the one of weight 4 because they involve less gates. So the error on the small stabilizers is about 4%, and on the weight 4 stabilizers is about 8%. And we find a reasonably good agreement with our numerical simulations that is based on parameters, on coherence parameters and gate fidelities that we've measured on this device. And so here you see that all the stabilizers work, but the error is on the order of has a scale of 4% for the weight 2 stabilizers and 8% for the weight 4 stabilizers. Okay, now you can, and the agreement with the master equations is good. And now you can put this together and try to run the surface code. As I mentioned, the surface code then involves measuring all 4 stabilizers in a single cycle and detect whether errors have occurred, and then decode that error information and try to correct for it. So here's the gate sequence that we've then implemented on our 17 qubits. So the gate sequence is implemented in 2 blocks. So in the first block, we implement all the Z-type stabilizers. So all the green plaquettes are implemented together by running the respective 2 qubit gates actually in different groups in the same time step, and running also the single qubit gates in the same time step. And then there's a second part of the cycle. It runs all the X stabilizers in a series of time steps. And what is important or what is useful in this kind of context is, while one type of stabilizers, once the coherent part of one type of stabilizers gets executed, we can actually measure the other type of stabilizers. And that's only possible if the measurement of some of the auxiliary qubits doesn't affect the other data qubits. And that's something that in our architecture with the individual readout resonators and the individual Purcell filters works particularly well. And another aspect that is important about our devices is that this readout time that you need to determine the state of the stabilizer auxiliary qubits with high fidelity, the cumulated readout time is about the same as the cumulated gate time for the stabilizer. So in many experiments, the readout is much slower than the cumulated gate time, and that would then lengthen the total cycle time and make the surface code worse. And because our lab has invested quite a bit of effort in doing good readout, this actually now pays off so that we have a short cycle time. And in fact, at the moment, we have the shortest cycle time of all the 3 experiments in superconducting circuits that exist between our lab, IBM's experiments, and the one in Jean-Wei Pan's group. And so what we then do is we prepare the logical ground state, the logical excited, and the logical plus minus states in a single cycle. So we essentially initialize the data qubits and then run the cycle once. And this deterministically prepares the desired logical state in the logical subspace. And then after the first cycle, you continue on and measure more cycles, and that you can then use to preserve the state over the n cycles and see how quickly your logical 0 or logical 1 decays. And you remember we'd looked at the physical decay times for both superposition states and basis states in the very introduction for this talk. And you would now compare that to how well your logical qubit does when you've encoded it in this kind of complicated fashion and run all these gates on the physical qubits to create a logical qubit and preserve it. And the physical cycle time is about 1 microsecond, which is kind of fast in comparison to some of the other architectures like ions, for example. The ion trap experiment by Honeywell has a physical cycle time for their very nice experiment, which I think is 4 or 5 orders of magnitude longer than that, even though that their effective performance then normalized to time is similar to ours and maybe even a little bit better. Okay, and then one aspect that I think I don't have time to talk about, but I mention here is that leakage to non-computational states is important. And in our setup, we're able to detect these leakage states, and we're rejecting those leakage states in the surface code implementation. And the leakage probability per auxiliary qubit is about 1% per cycle currently. And when we run this for up to 16 cycles, this implements 800 single qubit gates and 400 2-qubit gates. So it's a fairly big circuit on 17 qubits with a depth that equates to this total number of gates. Good. So then you perform this experiment, and I guess maybe so we're coming sort of close to the end. Maybe I'll so now this implements the stabilizer measurements, and each stabilizer then indicates whether an error has occurred or not. And you see that by finding the auxiliary qubit that belongs to that stabilizer in the excited state. And you record that information and you parse that information into a decoder. And then that decoder determines from that information on which of the qubits an error has occurred. And then you use that information to correct the error in your recorded data. And so maybe if there's questions later in the questions and answers part, maybe I can say a few more words of the decoder, but I would now say, okay, that in the cycle, we detect the errors and we feed them into a decoding algorithm that actually runs offline. And then we use the information from that decoding algorithm to determine where the errors have occurred. And then in every single shot of the error correction experiment, we apply that decoding information to correct the state of the logical qubit to the one that we would determine from decoding the error syndrome that is indicated by the set of stabilizer measurements. And so the data that we've then acquired when doing that is we prepared the 4 states that I mentioned, the logical 0, the logical 1, and here at the end of each line, you see in which states the code qubits or the data qubits are prepared. For the logical 0, they're all in the ground state. For the logical 1, we apply the logical X operator to all qubits in the ground state. And then similarly for the plus and the minus logical state. And then we perform n error correction cycles. And at the end of n cycles, we read out the logical qubit either in the Z basis or in the X basis by essentially measuring the expectation value of this operator. And we apply the result of the decoder to that. And then we calculate from that the expectation value of our logical operator and plot that versus the number of cycles. And that's what you see on this next slide here, which is essentially the main result of this work. So what is shown is the logical Z operator, which is the product of the 3 single Pauli Z's, and the logical X operator, which is the product of the 3 single Pauli X's, versus the number of error correction cycles on the bottom and versus wall time on the top. And you see how these expectation values decay in time. And we find that the decay times are on the order of 16 microseconds, both for the logical Z and the logical X. And what is important to notice here is that these decay times are much longer than the cycle time. And the ratio between the decay time and the cycle time actually determines the logical error per cycle. So the likelihood of a logical error occurring on your logical qubit during a single cycle. And that we'll discuss on the next slide, actually. And the performance for bit flips and phase flip is about the same. So the logical T1 and the logical T2 are very similar. And they're in reasonable agreement with master equation simulations of what we would have expected the performance of this device to be based on its coherence properties and some measurements of the gate fidelities and the readout fidelities that we've performed to characterize the device. So now you could ask yourself, okay, how good is this? Is this what we wanted? So first, I think we were very happy to see that it works at all, that one can implement all this kind of complicated procedure to realize the surface code on a real device with 17 qubits and understand what is going on and evaluate the properties of this device and find that actually you're able to implement this error correction. So for further looking at how good it is, we determined the logical error per cycle by first calculating the logical error probability as it increases with cycles. So the logical error accumulates as you run more and more cycles. And from this accumulation, you can determine the rate or the error per cycle. And the error per cycle from the rise of this, the total logical error, is determined in our experiment to be about 3%. And so I think this is kind of an interesting number to see. This is assembling the surface code per cycle from gates that have a 1.5% error. And there's 24 of those gates implemented in a single cycle. And nevertheless, after decoding, you end up with a logical error of about 3%. So that indicates that your this process of detecting and correcting errors in the surface code in the superconducting device actually does work. And so there's now various quality measures that you can compare the different experiments to each other. So here's the 4 experiments that currently exist on distance 3 codes, the one with ions and 3 with superconducting circuits. And in the logical error per cycle, our experiment is doing best from the superconducting circuit one. It's a little bit worse than the ion trap experiment. But as I pointed out before, it's important to see that in the end, the wall time also matters, and the cycle time in the superconducting devices is many orders of magnitude larger than the cycle time in this ion trap experiment. And that's mainly because the ion trap experiment required moving ions around for performing the ion readout on the auxiliary qubit. So this maybe puts that into a context and shows how good our experiment is. But overall, I think it's quite exciting to see that within a year, there were now 4 different distance 3 experiments that were performed. So maybe finally, how good is this now? What does this error rate of 3% per cycle mean? So there's different things that you could compare it to. You can, for example, compare it to the 2-qubit gate error, which is 1.5%. And one of the reasons for making that comparison is, for example, if you can perform a transverse logical 2-qubit gate, then you could enact that by essentially running 2-qubit gates between pairs of data qubits. And then and you would define a threshold as when the error per cycle of the error correction on the individual qubit is about the same as the error that is induced by implementing the 2-qubit gate between the 2 physical qubits. And that's something that, for example, matters also in these ion trap contexts. And there was a nice work by the Innsbruck group that had actually realized a 2-qubit gate between 2 logical qubits in this transverse fashion, where this is the right quantity to compare to. And so to now understand how close we are to that threshold, we actually did simulations trying to see how much better our logical error would get if we improve all the physical error rates by a factor of 2, 5, or 10, and then see where that would cross over with this 2-qubit error rate. And we find that this happens somewhere at an improvement factor that is somehow somewhere between 1 and 2. So that shows that our device is likely slightly below the error correction threshold, but not very far, by maybe about a factor of 2. And in the meantime, we've also done poly error simulations, which confirm that interpretation. So we would say that the break even is within reach, and we're quite close to it, but likely not above it with our current device. All right, so and that's it. We have realized repeated quantum error correction in a distance 3 surface code with superconducting circuits, and this was one of the first experiment, and I've pointed out the 2 other ones. We have a fast error correction cycle time and a low error per cycle, and while we're maybe not above break even, we're fairly close. And then and then the next step, we would like to implement feedback in our experiment and reset our auxiliary qubits, and then also do logical operations on our logical qubit, and maybe understand better how well our logical qubit performs when we, for example, inject noise into our devices. So, and with that, I'd like to point out once more the great team that has worked on this. And this is our experimental team at ETH. And I'd also like to thank our theory collaborators and the whole team at ETH. And I think I need to drink a little bit of water for my voice to come back. All right, thanks a lot.
Yeah, thank you so much, Andreas, for the very nice talk with so many exciting results and putting so much effort to. Thanks. So we have actually a lot of questions, many from the chat. So the first question is from Natalie Pearson. And she's asking, you mentioned catching the leakage of the stabilizer qubits during readout in order to deal with it. I was wondering how you then deal with that leakage and how limiting it is.
Yeah, that's an excellent question. It's actually very important. So we do 3-state readout with our readout devices. So we discriminate that. And currently, in fact, leakage is rejected. Yeah, so the analysis is conditioned on not detecting leakage. Yeah, so that's a constraint because you post-select on some of your data, and the post-selection rate currently is about 1% per auxiliary qubit per cycle. That then accumulates to about 8% per cycle over all the auxiliary qubits, and certainly that's not what one wants in the long term. So you need to further suppress leakage in future generation devices, or actually implement hardware mitigation for leakage events that get detected. But that will make the circuits more complicated. You will probably need additional qubits for doing that, and I think that was not yet implemented in this generation of experiments. But it's very important, and in the end, you want to avoid needing to reject any data because of leakage. In deep circuits, that is just required.
Thank you. There's a question by Andreas Wallraff. What in your experiment is crucial for keeping the measurement times so small?
Yes, I think the most important aspect is, so our measurement times are around 300 nanoseconds in this device at 99% fidelity roughly, or with 1% error. We have realized previously on single qubit devices readout fidelities of 98% in only 50 nanoseconds. And the key component for that is, maybe just look at this summary slide here again, is this combination of individual readout resonator with Purcell filter. And the individual readout resonators are coupled very strongly to the qubit. And so that creates a large frequency shift of this readout resonator with qubit stage change. And the readout resonator is then strongly coupled to a readout line, and that has to happen through a Purcell filter to not induce Purcell decay on these qubits. And so this is something that we've started to work on more than 5 years ago and works really well, and that we could deploy on large devices like that in a way that the accumulated gate time is not shorter than the readout time. Yeah. So indeed, this is important. I think this is pointed out in the paper also. It's a really nice technical development that we had actually done initially for different purposes, but that then came in handy to be deployed in this context here.
Thank you. Another question from Jonathan Conrad. How does the expectation value of the stabilizers behave over time?
Okay, so one aspect that is maybe also important to mention, which I hadn't pointed out explicitly, is that we don't reset our auxiliary qubits. So at the moment, this is not implemented. So the error gets indicated by a change of the state of the auxiliary qubit. So when it goes from 0 to 1, it indicates an error, then it maybe stays in 1 because there's no additional error. And then if the second error occurs on the same stabilizer, it will go back from 1 to 0. And because we do that, there's a bit of an accumulation of error, because as time passes, when the stabilizer auxiliary qubit is in the excited state, there's an extra error channel by it decaying back down to the ground state. And that we do see slightly when we analyze our syndromes. And then an experiment that we want to do is we want to compare it to a situation where we perform reset. But the reset will also take a little bit of time because it has latency, and comparing these two instances will be interesting. And in a prior experiment with a smaller device, so even before this distance 2 experiment, we had done an entanglement stabilization experiment that included feedback. And there we saw differences in whether we were performing reset on the auxiliary or not.
Mm-hmm. And one from Alexander Cordier. How do stabilizer measurements coexist with the Zeno paradox?
how do stabilizer measurements coexist with the Zeno paradox? I mean, we measure the parity property of our data qubits, and the data qubits get projected into a parity eigenstate, yeah, no matter what happens, and so that in some sense discretizes the error. Yeah, you could also say, okay, you have a continuous phase error, yeah, and but the measurement sort of forces it to pick an eigenstate, yeah, and you essentially enforce the error, and then you can and if there was none, that's good, but if there was one, you can correct for it, yeah. So there's no problem with the Zeno paradox.
And another question by Jonathan Conrad: do you assess what P of M exactly is implemented effectively by the stabilizer measurement? Does this change over time?
One could look at the properties. So there's maybe different aspects. So it's an effective measurement that gets implemented by running this gate sequence and then performing a readout. Yeah, and you could obviously look at how the elements perform, and this is something that we've done in a lot of detail. Yeah, and also how the measurement performs and what kind of effects it has on these auxiliary qubits. And in principle, one could analyze the stabilizer measurement in more detail, and I think we've also done some of that, but we've not yet reported on it. Yeah, by, for example, doing repeated stabilizer measurements or different combinations of stabilizers that one can look at. It's an interesting question. I don't have a slide or so, or can say something simple about it now.
Another question from Andreas Osterloch: how about the single qubit error in comparison? For instance, Google, IBM run without correcting.
The single qubit error, which we have, is 0.1%. I think that's it's a pretty typical one. If you really work hard on it, you can probably get an order of magnitude better. I think it really depends on the size of the device that people look at. Usually with increased device size, kind of the average performance drops a little bit. I think this 0.1% single qubit gate error is pretty good. Also, the 1.5% two qubit gate error is fairly decent. There's obviously better performance on some devices. Also, I think IBM has some nice performance on some of their devices. So there's definitely room to the top. I think what was important for these experiments that it was somehow well-rounded, yeah, and one of the, for example, the Google gates are quite a bit faster than ours, but you don't win if you can't do your measurement fast, yeah, and so therefore in the end we had a well-balanced device which worked out better, and I think one other observation that one has is like, the individual labs are quite married to their two qubit gate architecture, which are different. Yeah, Google has tunable couplers between their qubits. We do a controlled phase gate by tuning both qubits into resonance with each other. IBM does a microwave induced cross resonance gate, and these one has to kind of work out all the little details to make this perform well, and typically getting to something that performs significantly better requires a significant amount of work. So fixing or changing two qubit gate strategy is typically a major decision for larger devices.
Okay, thank you very much. Maybe a super quick question just to finish before we are cut off from YouTube. So what do you think are the major improvements in the near future? Where do you see potential in your experiment?
So, I mean, there's one big problem that we're currently having is that our two qubit gate performance is limited by microscopic defects in our device. And these microscopic defects are kind of scattered through frequency space a little bit, and the worst qubits that are affected most by those have then bad two qubit gate fidelities. And this you see, for example, in this example here at the bottom, that this stabilizer is way worse than the others. And it's not that we do anything different, but this combination of qubits suffers more from these two little defects. So currently we're trying to improve our device fabrication technologies to get better two qubit gates by cleaner fabrication procedures. So that's the next step. It's maybe somewhat technical, but it's really one thing that is quite annoying when working with these devices. And so we're trying to improve on that.
Thank you very much. That's great. I'll pass the mic now to Andrew.
Yeah, well, yeah, thank you very much, Andreas, for the really nice talk. It's really interesting, and as you can tell from all the questions, I think we all enjoyed it very, very much. Thank you also to everyone who sent in questions in the YouTube chat. It was really great to have all of those. So we'll be back next month on the 14th of July, where we're really looking forward to having Roberta Cecily telling us all about molecular magnets. In the meantime, please follow us, have a look at our website, quantumscienceseminar.com, subscribe to the mailing list, and you can follow us on Twitter for all the announcements as well. And yeah, until then, thanks again. Thanks to Andreas very much again for the nice talk, and see you